Hi everyone. This presentation is about the comparison between integer programming and Metaheuristic-based methods to solve sectorization problems. This is a joint work done by these authors, and it's prepared for ODS 2020 conference, which is a conference about operation research, machine learning, and analytics. At first, let me talk about the outlines of this work. In this study, we address two models from sectorization, which are selected from the literature. In the models, compactness and equilibrium are taken into account because they are the criteria that most sectorization problems strive to satisfy. In the first model, compactness is the objective function and equilibrium is controlled in the set of constraints. While in the second model, the equilibrium is considered as the objective functions and the compactness is bounded in the set of constraints. The first model is a linear model, while the second one is a quadratic one. We solve the linear and quadratic models using Pulp and PIOMO libraries of Python respectively. In addition, the first model is solved using a linear solver in the optimization toolbox of MATLAB. Also, we linearize the second model and we solve it using the linear solver from the optimization toolbox of MATLAB. We also solve the models by a genetic algorithm, which is from the PIOMO library of Python. Models are also transformed to multi-objective ones and are solved by NSGA2 of PIOMO library. We do a comparison between the apply methods in terms of obtained solutions and computational times. The results will be used for a more effective design of a decision support system that is being prepared for sectorization. About solvers and solution methods. The first one is Pulp, which is an open source package in Python that can solve linear models. PIOMO is an open source package in Python that can solve linear, quadratic, and nonlinear models. IntLinkProc is a function in optimization toolbox of MATLAB to solve linear models. PIMO is an open source package for multi-objective optimization in Python. About the problem, sectorization aims to divide a large territory to smaller sectors according to certain criteria such as equilibrium and compactness. It has many applications in political redistricting, sales territory design, healthcare redistricting problems, and waste collection, and many other districting problems. Now, let's look into the models. In models, we have a set of points which are to be assigned to a predefined number of sectors. We consider Euclidean distance between each 2 points. We have a target number of points per sector. Each sector has a center, and also there is a parameter for tolerance of the equilibrium criteria. The decision variable is defined as xij. This decision variable is equal to 1 if point I is assigned to sector J. In otherwise, it's equal to 0. In this study, the compactness is defined based on the total distance of the points to the center of the sector they are assigned to, and in this way, the objective function of model A, f1, is defined to be minimized. Also, we have some constraints. Each point is assigned to only one sector, which is satisfied by this constraint. And also, at least one point is assigned to each sector, which is satisfied by this constraint. Also, we have an interval for our compactness, which is an interval of tolerance. In model B, the equilibrium function is defined based on the variance of the number of points in each sector, whose formulation is like this, where Qj are the quantity assigned to each sector J, and Q bar is the average sector size. So, to be minimized, f2, the objective function of model B, is defined like this. Also, similar to model A, we have some constraints. So, as mentioned before, we solved model A and model B using PULP, int link probe, and PMU for model A, and PMU and PMU for model B, whose results are summarized in this table. In tables, F stands for value of objective function, and ST is the solution time. We use benchmarks which are generated by authors. Here we present our results for 3 benchmarks in different size, which stands for small size, medium size, and large size. As said before, model A is a linear model, while model B is a quadratic model. That's why PULP is used to solve only model A, because PULP is able to solve only linear models. Also, int-link prog is a function from MATLAB optimization toolbox, is able to solve only linear model. But PMO is able to solve non-linear model as well as linear models. PMO is a library in Python which contains many metaheuristics. The metaheuristics are single objective and also multi-objectives. In this page, we only present the results for single objective models. The results of multi-objective models or multi-objective types of the benchmarks will be presented in our paper. As you can see here, Pulp in a time less than 1 minute is able to find optimal solution. These are optimal solutions. But the solution time for IntLink program is more than Pulp. Also, as you can see, PIOMO couldn't find an optimal solution even for the small benchmark. But the reason for this is the type of operators like crossover and mutation which are applied for genetic algorithm. If we change the operators, the types of operators, we can obtain better solutions. The improved solutions obtained by PIOMO and genetic algorithm of this library and other metaheuristic of this library will be presented also in our paper. This means that IntLink program couldn't find a solution for this benchmark in a reasonable time. For example, we defined 5 minutes as a reasonable time for solving a medium benchmark. But Pulp and PIOMO could find solutions in reasonable times. Also, for model B, PIOMO couldn't find a solution in a reasonable time for this model, which is a quadratic model. Here we have some conclusions for this work. We can say that Pulp and PIOMO have better performance than IntLink program. PIOMO has good performance in terms of speed for solution times, especially on big problems. Operators such as crossover and mutation, which are used in metaheuristics, seriously affect the result. In terms of achieving optimal results with basic operators, PIOMO doesn't outperform solvers. The results vary with different operators. In our paper, we will discuss the influence of operators on results. The results of multi-objective evolutionary algorithms such as NSGA2 and NSGA3 will be presented also in our paper. Also, we will add the results obtained by Cplex in our paper. We have an acknowledgement. This work is financed by European Regional Development Fund through the Operational Programme for Competitiveness and Internationalization Programme and by National Fund through the Portuguese funding agency FCT. And here we have our references. Thank you so much for listening to this presentation.